Okay.
Okay, so let us start today's seminar. So today's talker is Velasco-Sevilla Liliana Esther from the University of Bergen. And before starting, let me just briefly introduce your career. So she get a PhD at University of Oxford in 2004. And after that, she moved to the USA and a research position at the Michigan Center for Theoretical Physics, MI. And after that, from 2005 to 2007, she moved to the University of Minnesota. And also after that, from 2007 to 2010, she moved to Italy and ICTP. And then from 2010 to 2012, she moved to Mexico. And after that, now she's now in the Kias, South Korea. Is it correct?
Yes, I am
okay.
a visitor at
Thank
Kias
you.
and at Sequest as well.
Okay. Okay, so today she is going to talk about the refined de Sitter conjecture in non-scale supergravity models. So please start.
Let me correct. Let me correct. I mean, the current affiliation of Liliana is the Bergen University in Norway. And just she's on leave from the university. Is that correct, right?
Yes, and I am kindly hosted by Kias and Sequest here. So yes, I also use sometimes the name Kirsten because of my husband, and it's easier when we have to do family things. So you can see here my birth name here, Velasco. So thank you very much for the nice introduction. So I am in collaboration with Aida Rasulian and Magdi Torabian in Iran, working in some models of noise-scale supergravity in the context of the De Sitter conjectures. So let me tell you, I am a phenomenologist, and my collaborator her student are doing string theory. And we talked about this idea because we thought it was interesting from the phenomenological point of view. So probably, it doesn't move, I don't know. You have heard about these Swampland conjectures, but if not, I will give you an introduction. So this is the outline of my presentation. This is also, I will present the noise-scale de Sitter models, these the so-called redefined de Sitter Swampland conjectures in the noise-scale de Sitter models that I'm talking about, and the TCC, so this is the Trans-Planckian conjecture, and how we can save many models from the so-called swampland, meaning the models which do not satisfy these conjectures. And in the conclusions, I will give you more motivation of my work and some, advances in work of progress. So this is the introduction. So I don't know how much detail I can give. So maybe you can raise your hand if you haven't heard about these conjectures. I think you have heard, but if not, please raise your hand. So just to know the detail that I should get into. Okay, so no, nobody has raised their hand, so I don't know what does that mean. But the thing is that, some years ago, in 2018, BAFA and collaborators put forward an idea based on some observations of string theory. And these observations are that no consistent de Sitter vacua have been obtained using string theory. Many people have constructed vacua, de Sitter vacua, using string theory tools, but it has been agreed that there isn't a rigorous proof that these really appear in the context of a string theory, and moreover, they are stable. So this is a very bold result because many people have been working in this, in constructing not the Sitter vacua. And so they put forward this idea and they put it with the name of the conjecture. So this goes as follows. They state that no de Sitter minima are allowed, only maxima are allowed. So this in terms of a potential of a scalar field, it can be written in a very simple form. So this is this C constant is a positive constant of order of the Planck scale. This is the Planck scale. This is the potential. This is the first derivative of the potential. Or also it can be put in these terms as the second derivatives of the potential, again, a C prime a constant, which is also a positive order n Planck times the scalar potential. So this is the bold idea. However, we know that in 1998, the discovery of the accelerating expansion of the universe was observed. And this should be or could be explained due to a non-vanishing vacuum energy. And 20 years later, they came the observational support for inflationary cosmology, according to which the universe underwent an early epoch of near-exponential quasi-de Sitter expansion, which you can think it was driven by an inflaton field energy. So you are a theorist, a string theorist, and you have this, but you have some observations, and you cannot deny that at some point the universe really appeared to had undergone a de Sitter transition. So what do you do about it? So this gentleman received a lot of criticism, and so they put forward another conjecture 1 year later after the original idea, and they say, okay, we need an explanation based on fundamental aspects of quantum gravity. And they dubbed their conjecture as the Trans-Planckian Conjecture. And they say, well, in an expanded universe, these Planckian quantum fluctuations should remain quantum and can never become larger than the Hubble horizon. So the meaning of this, or the main consequence of this, is that a metastable de Sitter point can be compatible with this so-called conjecture as long as its lifetime tau is bounded by this expression. Here, h is the Hubble parameter and is related by the cosmological constant in a very trivial way. This is the way where d are the dimensions, and also times the logarithm of the Planck over the Hubble parameter. So they studied then for constructions, statistical constructions, what would be then the typical value of this tau in order to be compatible with what we observe. So this is the motivation. And they argue as well that a theory which is really, consistent should never run into the problems that inflation runs. For example, inflation is very successful and allows for field theory computations without relying on any Trans-Planckian physics. However, if you know you work in inflation, you know the Trans-Planckian problem. And the Trans-Planckian problem is if or comes when macroscopic fluctuations trace back to the Trans-Planckian wavelengths during inflation. And then this evolution, the evolution of these fluctuations cannot be extracted from the effective field theory. So when sub-Planckian quantum fluctuations become larger than the Hubble horizon, they can become classical and freeze, which would lead to the classical observation of sub-Planckian quantum mode, which is, of course, not compatible because you are talking about a quantum mode that cannot be classical. So put it into bigger terms and with bigger consequences, this Trans-Planckian conjecture states that these questions should never arise in a consistent quantum gravitational theory because sub-Planckian quantum fluctuation should remain quantum. And this is achieved, again, if you put this bound on the lifetime that I expressed in the previous slide. So if our universe is stuck in a metastable de Sitter minimum, it cannot be for an infinite amount of time. In particular, if you put by hand the value of the cosmological constant, which should be this by hand, and then put it into the formula that I gave before, this gives you a trivial bound of 2.4 times to the 12 years. However, as recent observations, we know that the life of our universe is about 1.4 to the 10 years or 14 billion years. And you may wonder, okay, what is the use then of this Trans-Planckian conjecture if it's giving you a larger time than the life of the universe? So many people agree that this is not a very useful prediction. So we need to construct models which give us more insight into the fundamental physics of them by computing more precisely this transition time. So I will talk a little bit about this after. So now I gave this introduction. So this is the motivation. And then I come to the second part because, of course, we are working in the context of no-scale supergravity. So this is also a fundamental part of our work. So what are these no-scale supergravity models? No-scale supergravity, yeah.
Excuse me, although the organizer is not interrupting, but let me interrupt and receive some questions from students because from now on we are discussing more technical. I guess we are discussing more technical stuff. So if there are any questions, it's time for you to ask. Any students and
in previous page, just to one page ago, yeah. I am very how to say. I have very no idea about the de Sitter space, but about TCC, the tau u, the the time of universe is smaller than 2.4 times 10 to 12 years. If that means if time passes, then that found, then universe go to infinitely universe go to something. I'm sorry. What will happen if time passes then that upper bound?
So then the TCC wouldn't make any sense. So you see, the statement of the TCC is this inequality. So you put what we have here by putting as the value of h, this value of the, well, this expression of the H as a function of the vacuum energy. So just putting this expression and the value of the Hubble parameter, this gives you this number. And this, you say, okay, then the TCC makes sense because it is saying that it is constraining theories such that if the vacuum energy has this value, then those theories are okay as long as the life of the universe is smaller than this value. So that's fine. For example, if it was bigger than that value, if the result of that formula would have given you 10 to the 13 years, then the TCC wouldn't make any sense because it's saying the TCC is stating that the value of the life of the universe, it is bigger than we observe. But okay, so it just says now it should be smaller than this. However, we know that the actual estimated value of the lifetime of the universe is this one, 10 to the 10. So it's 2 orders of magnitude below. So it could still be that more refined statements of the TCC can give you a value between 10 to the 10 and 10 to the 12. And that again would mean that the theories, that statement of the TCC doesn't make any sense. So that's why it is important to construct more specific models which can really tell you a more detailed, like a better computed bound for this value. So for example, let's imagine I have a model in which I discover that the value of the TU is 10 to the 9. That model will be compatible with the TCC because it's less than this, but rule out because it's bigger than the life universe. So that's, I don't know if that clarified your question.
Yeah.
Liliana, this is Francesca.
Ciao.
Can I ask you, ciao, can I ask you a question which probably goes beyond your expertise, but I'm a little bit confused here. Now, this is a conjecture, so it is not a rigorous derivation from string theory. Just conjecture for me, it's something like a guess that you get out of your theory somehow. In being a conjecture and not a rigorous result from string theory, why would I have to believe that?
That is a very good point, and this is also my point as a phenomenologist. However, there are many, it's not just by hand, let's say. There are many ideas which can support it, and it's true that the ideas supporting this go beyond my expertise, but they are nicely explained here.
There are several. It is a sound conjecture, you're saying.
It is still a conjecture, but it is a sound conjecture. However, as you see, the reason why it's many people is like skeptical about this is because exactly doesn't help you much, right? It is giving you these values.
It's sort of a loose bound, loose because we are way below this length, this time length. So, of course, if, as you said, if we were 10 to the 13, I would be worried. But because we have at least 2 orders of magnitude, it's a loose upper bound, which. But it will be interesting, provided one can be sure that this is a strong prediction somehow.
Exactly, and they are working on that. I think an independent group, so the Valley, also is working on that. They are converging to the reasons of why, and this is due to the consistency of gravity near a black hole. So there are supports from many points of theory construction. So it is unlike that the refined de Sitter conjecture. This TCC is not a wild conjecture because if you see carefully the refined de Sitter conjecture, it seems just a statement. But the important point is that in this paper by Baffa, they show that in some cases the TCC leads to this refined de Sitter conjecture, and the proof is not general. So, for example, in our work, we prove that it does for our specific setup.
Okay.
I think I have more familiar with TPC conjecture for inflation, limiting the number of wave foldings. So, I mean, there's fluctuations. You want the sub-Planckian fluctuation to be classical, but not the Trans-Planckian. You don't want the Trans-Planckian fluctuation to be classical. So then there's a limitation of number of wave folding during which the quantum fluctuations will exit the horizon. So can you comment on that? I mean, I know that there's a dependence on the reading temperature. Also, there's a kind of competition between number of wave folding than you need, and then this TPC conjecture, right?
Yes,
it's a upper bound on the number of wave folding.
Yes, as far as I know, this bound comes exactly from what you said. And this is that you want all the quantum modes to remain quantum. Because if you exceed certain number of e-folds, then you can get into the classical limit. But as long as you satisfy this, that never happens.
Yes.
So
that's this lifetime because for the inflation is taking place for a short period of time. So I'm thinking that just the number of folding, the bound on the number of folding, is nothing to do with the bound on the lifetime of the universe. So I don't know.
It's not linked, you mean? Or?
So because I don't know, maybe you are thinking of different distal phases. In the early phase for inflation, and then late time, I mean, the current universe is vacuum domination. And there are two distinct distal phases. So if I'm talking about early distal phase, the only bound from Trans-Planckian conjecture is the bound on the number of wave folding. So,
yes.
So is that it's not the same as the lifetime bound, no? Just let's say if you have a number of folding 50 or 60, and then you have a full access to quantum fluctuations, including Trans-Planckian ones. But if you reduce them, I mean, then the quantum fluctuation, there's nothing, no quantum fluctuation. There's no time for the quantum fluctuation to exit because inflation, the period of inflation is reduced, right? So there's no issue about Trans-Planckian mode from the first place.
Yes, I agree with that. But as far as I understood, imposing this bound ensures that that never happens, and this can be translated into the number of e-folds. But that depends on which theory you have as well.
Because normally, if you reduce the number of folding, you are in tension with a spectral index. So you need to come up with a particular model to make your expectation to be consistent with the observation. So, my another question is about the refined de Sitter conjecture. So I tried to follow the earlier version before refined, but I got confused after refined. So what is the current status about this conjecture? It's just it's not and, it's an or, right? It's a first or second.
Yes. Yes.
So, is there any constraint? I mean, from this, do you have any constraint on dark energy or inflation?
Yes, I mean, on dark energy, there are some constraints. On inflation, no. I mean, it depends on the model, but on dark energy, it's easier to have constraints. So I will talk about this a bit later, but because you have been following, so this first redefined de Sitter criteria is the original one. So in this original one, they say just the first derivative should be bigger than this value. And then they say, okay, it's maybe not complete. Maybe it can also allow for this, the second derivative should be negative. So we know if the second derivative is negative, we have a maximum. But it could be a de Sitter maxima. And they found that also these kind of potentials are still allowed because before they were ruled out. And many people have worked on this. And the examples that I'm going to present basically satisfy this second criteria. So you can either have this or this one. But I think that in many cases, C prime is difficult to compute. So you may think, okay, this is an arbitrary constant that you could put by hand. And what we found is not, but it's difficult to compute it precisely. So then to summarize, the original form is what it was this one. So it ruled out completely this de Sitter, complete de Sitter potentials. So that means potentials which are positive and have de Sitter vacuum. But with this refined, it now allows the Sitter potentials, but with maxima and not with minima.
So the minimum de Sitter vacuum is not allowed by either condition.
No. It should you should have in your theory the anti-de Sitter vacuum.
Okay, so it should be, but the rolling potential like a quintessence potential might be okay.
Yes, that's right. So I will show examples of this kind.
Thank you.
May I continue? Yeah.
May I ask one question? Hi, Liliana.
Yes.
Just out of my curiosity about TCC, maybe in the next page. So I'm curious about the TCC in a kind of extreme case. If you have an infinite number of vacua, maybe we can imagine a reduction type potential. There are small wiggles on top of the linear potential, and the vacuum is, undergoes multiple transitions from the other. But each transition satisfies this condition. But if you proceed, many times of transition, and then in total, it could be out of this condition. Can we say something about such situation from this conjecture? Is it also not allowed?
I think it is allowed. So let me see if I understood. So you are basically imagine like kind of a potential which is going down
Yeah.
at different steps.
Yeah.
It is allowed because the basic shape that is allowed is that you have a maxima at some point, and then you can always go down.
Yep.
And it's this kind of also called metastable de Sitter because as long as it has an anti-de Sitter vacuum, that's perfectly fine. So that's the only condition. So it doesn't matter on how many steps you go down. It just matters that at the end you have an anti-de Sitter vacuum.
I see. All right.
I
Okay.
think that's an interesting question. So normally, once you're trapped in the local minimum in the relaxation scenario, the lifetime of this local minimum is thought to be very large, and you're just stuck there, don't move along. But if this conjecture is true, then the lifetime on this is the short, and then there should be a constraint on the curvature.
Yeah, of course. Yeah, that's true. But I mean, you can always build it so that the minimum is not stocked in. So you are not stuck into the Sitter minimum. Yeah.
Thank you.
So this also, it's not a classical rolling. Maybe there might be tunneling because the local minimum, you don't have an access to the other minimum classically, but there is a quantum tunneling process. So you have a probability to exit to the other minimum. So
Yeah,
then in that case, you need to consider lifetime of the vacuum, right?
Exactly, yeah. Yeah, this is something that I will talk about a little bit later.
Okay.
So, yeah, should I continue? Yes?
Yes.
So
Sorry.
the second part is this no-scale supergravity. And I was saying that these are from in market since long time ago in 1984, and the fact is that they are very predictive, at least from the phenomenological point of view for particle physics and for inflation, and they are very nicely written. So you have the basic elements in supergravity, the Kähler potential, the spur potential. You can have these gauge kinetic functions, but you begin with something which has gauge kinetic functions which are trivial. So the typical form of the Kähler potential is this -3, a positive constant A, and a logarithm of some fields, so scalar fields. And then you can construct this de Sitter, actually, or anti-de Sitter potentials, playing around with this A and these powers here. So these numbers are constrained by these relations, but this A actually being positive and negative allows you to construct many things. So as I said, they are very nice, very predictive, and the good thing with supergravity, you can compute everything. So you start with this potential, which is called G, which encompasses the Kähler potential and the logarithm of potential and the super potential. And you can see the scalar potential, it is written in a very compact form. So the e to the g is this quantity. X is just derivatives of the g times the Kähler inverse of the Kähler metric, and 1 minus 3. So I find it that this is very nice, and you can compute it in a very compact way. So for one field, it has this expression. So you can take the derivative, and this is an exact form of the derivative. And immediately you can see the conditions of an extreme value. And this then is the condition that along the real axis, you should have an extreme value. However, it can be typically not a minimum, but a maximum, because when you plot this scalar potential along the x and y coordinates, it shows you that it has along x is just this constant line, but then along y it is maximum. So from the theoretical point, particle physics theoretical point of view, you don't want that, because we base our theories in constructing a minima. But these are exactly the kind of suited potentials for this kind of TCC. So before going there, let me show you this, that since 84 to these days, Ellis and collaborators have been working on stabilize this kind of potential to really apply this to particle physics and inflation. So they found that with adding this quartic term, in this example, instead of putting phi, I put t, but of course it's just a scalar field. And then just by adding this, the form of the potential switches from exhibiting a maxima to really allowing for a minimum. And this is the very nice potential that in phenomenology we like, because yes, it's a minima, then you can calculate masses, you can draw your phenomenology. And in fact, based on this, you can apply it for inflation, and they have applied for inflation adding this. Actually, we have a collaborator of Olive and Ellis here, Bunyan, has been also working on inflation. That it's very nice that you can reproduce the Starobinsky model, and just based on how the freedom that you have to select the value of lambda and the value of this mass parameter, you can get different, plots for v over m squared. So you see, for example, this ratio, square root of 3 lambda over m, 0.99, and so on. And you see that an interesting case happens when this ratio becomes 1, because this is in agreement with what it is observed. So this is at the typical plane, plotting the spectral index ms against this tensor to scalar ratio. And these are the limits imposed by W and Planck with this bicep 2 and kept at 68 and 95 confidence regions. So 68 is this blue, and this 95 is this lighter blue. So you see that exactly when that ratio is square root 3 lambda over m is 1, you are there in the 68%, and with some others you are almost there. So that's why it's a nice value. So this is what a particle physicist phenomenology would do. Just forget about awful potential and find a way to find a de Sitter minima. But as I said, when you compute it, this gives you naturally, without doing anything, when you compute this second criterion, basically to compute this, you have to compute the Hessian of this potential, gives you a very nice formula for the imaginary part. So, and this formula, you can understand it, so maybe, so this is the formula that you get, and you get that it's naturally negative. So if you don't do anything, it's negative, and there you have a candidate to really explore this, the Sitter conjecture and the TCC. So, however, you have to do something because this TCC conjecture is supposed to make sense only with theories which are effective theories. So in your effective theories, you need to have all your fields canonically normalized. So in order to canonically normalize your field in this theory, you have to add a quartic term. Notice that this quartic term is not the difference, but the sum. And this sum is important because it doesn't stabilize the imaginary part, meaning it doesn't create the de Sitter vacuum, but it just really fixes the real part to one value. And then you have a theory which is physical, effective, and at which you can apply for which you can apply the TCC. So you notice that the form of this imaginary part basically doesn't change because the functional form of this 5 minus 1 constant minus this 5 and some other constant is the same. So, but you have to do it. So once you do it, then you come back again to this kind of potential, the kind of shape you started with, which exhibits a maxima and not a minima. And there you have a theory where you can compute the TCC. So then what we did in this work, which is now published, then we studied for different values of this alpha parameter, which values can give us what we were looking for. So what we are looking for is the Sitter maxima, and what we don't want for this is the Sitter minimum, like this one. So for depending on the values of alpha, then you see that you can find some conditions. So since this theory is not specific, the TCC we can say only in which region of our parameter space is satisfied. So, so these are more details about how to calculate this Trans-Planckian conjecture. So basically, the starting point is the Friedman equation, and this value, the bound on the tau that I written in the on the slide of the TCC, basically translates into the scalar potential to this formula. You see, you just have to calculate the derivatives of the potential and see that this inequality, it is satisfied. So this is this computation is not technical actually, and you see it is written in a very simple way in terms only of quantities of your scalar potential. So what and for which we already have them, because calculating the imaginary part of this scalar potential is calculating this basically the second derivative. So for some values here, we found that this TCC is compatible. So I forgot to put it here on the slide, but this is, let's look at this plot on the right hand side. This is for alpha 25/9, which gave us the Sitter maximum. And we see that not in all the regions of the parameter space, this is the TCC satisfied. If you see on the scale of this parameter, you can argue that only in a very small region, this is satisfied. And of course, when you have the scalar potential negative, you don't have to do anything because you are in a region where you have an anti-de Sitter space. So everything there should be fine according to this Swampland, criteria. So you see, it's not trivial for some cases to find a region where the TCC is satisfied. We found it here. And what I want to stress is that you see, this is a theory which is very easy to compute. but it gives you insight of how difficult or how easy is to get such a configuration. And in this case, it was easy. So, so now, of course, as we have been arguing, the value of this lifetime is not of any use because there is a very loose bound, as Francesca just mentioned. So what we are doing is that notice this potential. We are currently doing this. So this is a potential in which we still have this de Sitter maximum, but we have some anti-de Sitter minimum. So it crosses the zero region here. And as Hyun-Min was saying, we can go from here to here, just a rolling lifetime, or we could, you know, from this point, construct a de Sitter minima, and from that de Sitter minima, calculating the tunneling. So we are currently analyzing these two kinds of potential. One, the rolling time, that also should be constrained by this TCC, and the other tunneling time, from which we could start from the Sitter minima. So yeah, we have not finished, but we are hoping that it really gives us a tau that it is more constrained. So that's our hope. So the other motivation of the work that we were doing is that we noticed when I started this work, this paper by Ferrara and collaborators, in which they studied for a list of supergravity models how the first criterion or the second criterion could be compatible with supergravity. And what they found is that basically a recipe to fix any supergravity theory that you have in order to get it to satisfy the second de Sitter criterion, at least in some parameter space. So basically the recipe was the following. Take your original supergravity theory, put instead of this original Kähler potential, such a term with some Q constants, positive constant, and some additional field. Then do a multiplication of your potential by a power of this field, and then find a region, just playing around with this Q and P, for which this second criterion or first criterion could be satisfied. So what they double rolling dynamics, because in fact in one direction, the direction of the chi is rolling. So again, as it is supergravity, you can construct in a very nice way all the quantities. And when you construct all the quantities, the potentials become like this. So this is rolling. It's if you cut and slice, you will find just one curve going down. And because it is going down, it has this behavior that we are looking for. And this is an easy way to be compatible with this redefined de Sitter conjecture if you want to construct such models. So what we did is then we apply it to our no-scale construction. And for our no-scale construction, we can do many things in this paper, first papers that we already have published. We did many things. We added many fields here, or we added other fields, rolling fields. But the reason I'm talking about only about the addition of two extra rolling fields is because this has a natural application to quintessence. So quintessence are basically models of a scalar potential with a scalar fields, which can give you an explanation for the dark energy. And this can also explain the accelerated rate of expansion of the universe. So basically, you see this is the form that we get with our no-scale de Sitter construction. And so this is the potential that we get. And this is exactly the form that is needed for quintessence. So it couldn't be easier, right? Because it has two terms with one field and the other term with another field. So it is exactly this. So then this can really then explain dark energy up to certain constraints. So again, these people studied before which are those constraints. So let me go directly there, because in this plot, this black line, it is the line bound satisfying the observations from bicep baryonic acoustic oscillations and the supernovae. And they tell you that if you have a model of quintessence with these exponential factors, then everything is allowed as long as it goes below this black curve. So you need two terms because you need to fit two regions, one for a late redshift and one for an early redshift. But if your theory is able to be below that in all the regions that you can construct, then your theory is in agreement with this observation. So you see that if you had a theory with this lambda parameter 1, then this will be disallowed. But as long as your theory is below this, then it's allowed. So they have this value of 0.6 then. So then I have to say that in these papers by Ferrara, where they analyze many, not many, but the most representative supergravity theories, they couldn't find a way to put less lambda parameter above 0.6. But in our case, it's possible. So that means we found that in no-scale de Sitter, you can find playing around with these two terms, models for which these you find a region that with the values that you exactly need, meaning that lambda or gamma parameter should be 0.6. So this is one highlight of also of our model. So so this I will go to the conclusions already, but to give more time for more questions that you have. So what we found then is that these no-scale supergravity models provide a great scenario to test the refined de Sitter conjecture and the Trans-Planckian conjecture. And we explored minimal, and we found that it's very nice, very easy to analyze. And we are looking forward to understand implications out of this scenario. So let me remind you then. So these original de Sitter plateaus arise naturally in no-scale models, even with one field. But as I mentioned, from the phenomenologist point of view, you want to build up models of inflation or models of description of particle physics. You want these models and you want to really create the Sitter minima. But if you don't want, and if you want to analyze or pursue implication of this Swampland conjecture, these are the models that you want to analyze. So as I said, there is no use of them if you don't have more specifics about your model, or if you cannot get down this bound on the lifetime coming from the TCC. So as I said, we are working on computing in one case the lifetime and the other case the rolling time, because I think this will give us an insight. And why do we want that? Because you see, when you have the Sitter minima, even if it's not stable, you can construct in this, the Sitter minima, your particle physics models, and then you can do all the particle physics there, but at the end you say, okay, this is not going to last forever, and then you can give the lifetime. So basically what we're doing is just finding a region in which our potential looks like this, but in another region which it is like this, and then apply all that we know about phenomenology of particle physics. And also this idea of the rolling dynamics, we see that it works. We saw that in this scenario of no-scale de Sitter could really explain these quintessence models. But Cuneo was so kind to me to refer me at some point before completing this work, this reference. And these people studied a long time ago that in supergravity models, it appears to be difficult to construct quintessence models. Either are trivial meaning that you have just a potential, that your quintessence potential will be the potential equal to a constant potential and the exponential factor, or that is not possible to couple to the rest of matter. In either case, you are not going to be able to derive any constraints on other aspects of the theory, because if it doesn't couple to the rest of matter, then you can describe quintessence without having any implications for particle physics. So of course that doesn't help much. So I mean, we analyzed this paper, and as far as I understood, it's not a real proof. It's just like a series of arguments. So there is a debate now in this community of Baffan et al. Of whether or not this is really possible to construct such quintessence models in the context of supergravity. So yeah, thank you. That's yeah, what I wanted to share.
Thank you very much. So if you have any question or comment, please.
So I have a question on because we have an inflation model and quintessence, and for inflation, is your concern is you are not. It is not enough to have stable distal space in the true vacuum because of this refined. Refined distal conjecture, right? You want the distal minimum to be unstable. So then my question is is it possible to have inflation at the same time the quintessence?
Well, theoretically it's possible, but it's not necessary, because with inflation you are going to be already describing the expansion of the universe, and you just need a candidate for the dark energy. Of course, quintessence gives you that candidate for dark energy and explains the expansion of the universe, but you can perfectly have inflation without quintessence. It's not.
If you have a massless scalar field during inflation, maybe you might produce some isocoverture perturbations. Apart from that, suppose that you have a massless, almost massless scalar field, like because of the shift symmetry in the Kähler potential, but somehow you are generating a potential by a small amount, such that it doesn't influence inflationary dynamics. But does it play a role for quintessence field in the late time somehow? Then and then you are a minimum after inflation. You roll down to the minimum of the potential, but that minimum, the potential is not, it's the potential for the inflaton, but there is minimum for the inflaton, but it would not be the minimum of the it would not be the minimum for the quintessence. So then you can avoid the refined. You can satisfy refined de Sitter conjecture, right?
Yes, that's a possible scenario. If you see this as I mentioned, this kind of potentials, in which you construct here at the top such a minimum, can give you that, because you say, okay, in this minimum that I construct here, I can have inflation. And then when it goes down or it tunnels, it wouldn't have any role. So I think it's possible, yes. So the first part that we are doing is that we are constructing this and then calculating these times, because if those times are not in agreement with what we observe, then the answer would be no, it's not possible to construct. But as far as we are looking at, it just depends on the choice of parameters. Yeah, I mean, yeah, the idea is very interesting, but what? Just one question. Why would you like to have a still quintessence if you already have inflation? So,
yeah, if you have inflation, you are satisfying refined de Sitter conjecture during inflation because of slow rolling, and when you go to the minimum of the inflaton potential, you are breaking. I mean, you are violating refined de Sitter conjecture because we are in the another de Sitter phase. So it might be natural to think of unstable de Sitter vacuum after, I mean, in the end of inflation, after inflation.
I see now.
So,
yeah, no, that's I think.
And also, I don't know. I didn't work much. I noticed that there's a H0 problem, H0 tension recently, and people talk about several solutions to that. And one of the solutions is the early dark energy scenario. I don't know if it is possible to make early dark energy to be dominant before CMB scale and let it roll down to the minimum of the potential, but still might be rolling, but I don't know. In your scenario, you have several rolling fields, so I don't know. Does it?
Yes, I think with several rolling fields you can do something about, but we haven't done. But with one, of course, with two is impossible, because at least you need a third one, apart from the two to describe the late and not so early universe. And then you would need to add another third one for the early phase. I think that's possible, but we haven't studied that. But I think it's something that it should be studied. Maybe we can do it together. But we haven't pursued this because I think there's, I'm not sure, but this Hubble potential, I hope it resolves soon. Yeah, due to the calibration of Cepheids, but I don't know. I mean, certainly it could be a possibility. So, but I mean, I like more the idea of combining quintessence and inflation. So we can work on that.
And then also, I'm curious about the impossibility of coupling to matter. I mean, coupling the quintessence field to matter in supergravity. You said the early work by Brock and Martin in supergravity, it is not possible. Maybe it's not. Maybe it might be fair to say that it is non-trivial to couple the quintessence to matter field that was just a statement, right?
Yes, it's no. Okay, let me see. It's trivial to Copeland, but the problem it has some problems with the already bounds on the masses of supersymmetric particles. So it is possible, but
trivial. I said trivial to couple. I thought that it's not. It's
yes,
impossible.
is either trivial, meaning that it just has this form of the scalar potential, which is a constant times an exponential factor, but then it doesn't tell you anything because the scalar potential is zero. Or it's not possible to couple.
Trivial in the sense I coupled to gravity.
Yes, trivial coupled to gravity and just this form of constant potential. Or not possible to couple to the rest of matter because it can couple, and in this paper they show they can couple, but it doesn't satisfy the particles, that the masses of the particles are way too light, or depending on the theories, there are other problems happening.
I see. It's a phenomenologically acceptable scenario.
It's not phenomenology, exactly.
It's not acceptable.
Yes, I mean, I think you know, you really need a heavy phenomenology to rework on that statement because they put it as a novel theorem. But I think there could be ways around. So, yeah, but, you know, phenomenology, I always think is much more complicated than theory because you have to calculate lots of parameters.
Yeah, there's the best parameter space.
Yeah, there is a lot of parameter space to study. So it's work for, you know, heavy worker phenomenology. Maybe, I mean, if you see these Hubble tension results and quintessence is still, you know, a nice theory to explain dark energy, I think this should be worth to analyze. Because of course this statement is quite bold. So it may be just possible to analyze it case by case. Yeah.
Okay, maybe Shuntaru, you may receive other questions.
Well, I have sorry, I have some comments on the questions regarding the quintessence case. First, well, the trivial difficulty is that just imagine gravity mediation, then a quintessence field got a SUSY breaking mass about a gravitational mass, which has potential like a quadratic on top of the exponential potential. That makes the quintessence scenario hard. I mean, it's diminishing. And at the same time, I'm worrying if you have such a quadratic contribution from the SUSY breaking, the potential is stabilized with some non-zero value, which is de Sitter vacuum due to the SUSY breaking effect. Is there any way out to avoid such a de Sitter appearance of such a de Sitter vacuum?
Yeah, but this conjecture says there is not a problem that you have a de Sitter vacuum. It's just a problem if you don't have an anti-de Sitter vacuum. So at least with this kind of let me show you. With this kind of models, well, not you have to multiply many other fields, so phi1, phi2, and so on. You can construct potentials in which you have de Sitter minima and anti-de Sitter minima. So, if, for example, imagine that you write this quintessence model for such a theory. So you're saying that then you have a de Sitter minima and you may be there and describing your quintessence theory. But as long as there is a way to go up to the anti-de Sitter, there wouldn't be any problem according to this refined de Sitter conjecture. the problem is how to calculate it, because you have to. I mean, this part is not that difficult, but then you have to calculate the spectra, and they have to be sure that the lifetime it really allows you to go to this anti-de Sitter vacuum. But yeah, definitely, it's a very interesting question. So
Well, yeah. Well, I have another question, which is about the inflation part that you first had to talk. So you have considered a phi and phi bar, which is stabilized by this quadratic term in Kähler. B or 1 over L. So somehow stabilized by some scale L. So it's a sort of somewhat conceptual question, but if TCC says that M Planck is a sort of cutoff scale, but now you have another cutoff scale, which is L, the stabilization scale. So I thought the quantum fluctuation beyond this cutoff scale doesn't make sense anyway. It doesn't reach the Planck scale anyway. So I'm a bit confused.
Yes, I mean, in these scenarios, so, okay, let me see if I understand correctly. So you're saying, because, yes, you see, you know that this B is in reality a constant over a scale. And you're right that that scale should not be above the Planck scale, because of course it wouldn't make any sense. So so as far as I see in these theories, you wouldn't incur in going beyond the Planck scale, because in any case it doesn't make sense. And I totally agree. But the TCC is not simply going beyond the Planck scale. The TCC is that, suppose you already have a de Sitter minimum. So is it within the lifetime of the universe possible to go to an anti-de Sitter minimum? And if it's possible, then your theory doesn't have any problem. So yeah, there is two different things. Yes.
I see. Maybe my question be stated in another way. We see a Planck scale in a TCC condition, the conjecture, but why is it? Should it be M Planck? Can it be like a theoretical cutoff scale, sort of?
I think it could be. Now that you put it in that way, I think it could be. I mean, the Planck scale is there because, of course, you want to write it in terms of some quantity that is fundamental, and it's fundamental because it's the gravity scale. If you put another scale, then they should argue why that scale is fundamental.
I see.
I see there's a logarithmic dependence on the cutoff scale on the lifetime bound, and it's log of cutoff. Maybe it's not that sensitive to the choice of cutoff, but if the cutoff scale is very small, then I mean, the bound is more, stronger.
Yeah,
I think the cutoff scale that the Kunio was talking about is the including gravity. So if you have a new particle, you cannot describe physics beyond that scale. So including gravity, if you maybe decouple gravity from your theory, if you don't know how to describe beyond the new scale, it's better to put the cutoff scale at that massive scale, right? So, but I see that there's a logarithmic dependence. So.
Yes, I think numerically wouldn't make a lot of difference. But the thing is that to write it in terms of a fundamental scale.
I see.
Probably inflation itself would make sense, would not make sense if you have a small cutoff, right? So including gravity, I mean, if you cannot trust effective field theory below Planck scale, you cannot trust inflation in the first place. So I don't know
Right.
if it's a problem with the B parameters on small scale in the theory.
No, as far as I remember, the B parameter, well, the cutoff scale should be 2 or 3 magnitudes smaller than Planck scale, but which is still bigger than gut scale, so it doesn't have, it doesn't affect the inflationary dynamics. So, yeah, nothing wrong with such a.
You can still trust quantum and the kind of it is sensitive to quantum corrections. So
right. Yeah.
So yeah, if any of you are interested to work on these things, let me know. A lot of things can be done, as you can see. And as I said, from a phenomenologist point of view, is that you really need to extract what are the consequences that you can have to other aspects of the theory, meaning about some masses of some particles or couplings. So that is what it makes sense for me, of course, as a phenomenologist.
So can I ask a small question?
Yeah.
I don't know, I could understand the part, but it seems in your slide, the chaotic coupling B is constrained by TCC. Is that correct? My understanding is correct? In your, I forget which part, but you show the plot.
Yeah, I see. This is.
B is not chaotic coupling.
This is because I show different things. This is not to stabilize the imaginary values to stabilize the real direction, and B is the value that the real direction should get in order to be canonically normalized.
So TCC constrained the vacuum expectation value of pi.
Yes, that's right.
I see. I misunderstood. Okay. Actually, I wonder. So if you relax this model, I mean, if you apart from the no-scale type, then what TCC can say about coupling or vacuum expectation value? So
I don't know, because you have to study case by case the parameters.
Case by case.
Because I mean, in general, of course, your current potential depends on many parameters, so you don't know the TCC which one will constrain. In this case, it constrains this because this is not fixed. So you just can see what are the constraints of it.
Okay, thank you. And also, I'm not so familiar with this kind of conjecture, but this year I found a paper which states about gravity no mass conjecture. I think so. It's related to the series of the conjecture. So, do you know about this, or do you have opinion about it?
So, do you remember?
If I remember correctly, the gravity mass conjecture states that gravity, gravity mass is has lower bound, I guess.
I mean, it's the bound on the Hubble parameter. You can say in the other way around, but you're not exciting gravity, during preheating or reheating period. So there is upper bound on the Hubble parameters. as I remember. It's related to particle production, right?
Yes, yes, yes.
Yeah, if I remember
Heavy
correctly.
gravitational.
Yeah. If I remember correctly, the gravitational mass is bounded by the Hubble to some power.
Mm.
Yes,
Yeah,
I think it's
yeah. So yeah, I wonder this kind of model is how to say. If we apply your model to such conjecture, I wonder what is happening, or it's
Yeah, this
consistent
is
or not.
a toy model, because you see our model is just a scalar. So in order to see the gravitational, then we have to add particles and see. But the good thing is that in this no scale, you have a very fairly robust prediction about the gravitational mass. So it may be not that difficult actually to
Yeah.
do.
Okay, thank you.
Yes, thank you to you. It's a very nice question.
Any other question or comment? So if not, let's thank Liliana